Greetings everybody, and today we're going to be deriving the Gauss representation for the gamma function. So this is quite an important result because you can then use it to derive the Euler and Weierstrass infinite product representation for the gamma function, and you can use those to study some interesting features of the gamma function itself. So let's just jump straight into the derivation. We're going to be starting with the integral definition of the gamma function. So gamma of some complex number z is equal to the integral from 0 to infinity of t to the z minus 1 times e to the minus t dt. And from here, I want to make one small, or not small, but one replacement on this exponential function. Notice that if we have e to the x, well, one of the definitions of e to the x is the limit as n approaches infinity of 1 plus x to the x over n to the nth power. And we're going to be making this replacement inside of this integral. So notice our x in this case is minus t. So if we plug minus t into here, we're going to get the integral from 0 to infinity of t to the z minus 1. And then now we have the limit as n approaches infinity of 1. And then x is minus t, so we're going to have a minus t over n raised to the nth power dt. Now what I want to do is I want to drag this limit outside of the integral, and this is pretty much an interchange of limits, and in order to justify that you will need to show some kind of uniform convergence on the integrands, but I don't know how to do that properly, so I'll leave that up to other people to justify. But assuming that everything works out nicely and whatnot, we can just drag this limit outside the integral, and we're left with the limit as n approaches infinity on the integral from 0 to infinity of t to the z minus 1, and now we have 1 minus t over n raised to the nth power dt. And now I want you to notice one small detail. Notice that n is approaching infinity, so it wouldn't really hurt if we replace this infinity with just an n, because in the end, well, this n is going to turn into infinity anyway. So this is the same as the limit as n approaches infinity on the integral from 0 to n of t to the z minus 1, 1 minus t over n to the nth power dt. So as you can see, as n grows bigger and bigger, we're just going to end up with the integral from 0 to infinity. Okay, so this is what we have so far. We know that this expression is the same thing as our gamma function. So I'm just going to write it at the very top just so we have a little bit more space on the bottom. And next, what we're going to be doing is we're going to be doing some integration by parts on this integral. And this is going to be probably the most trickiest part of this video. So we have this integral, and we'll just place it there, and we want to perform some integration by parts a number of times. So I'm going to be using the di method. So this is a method that is used by Black Pen, Red Pen, and many other people. You can check out Black Pen, Red Pen's videos on integration by parts. That's where I learned integration by parts using the di method from. So yeah, check out his videos to learn how this method works. But essentially, we want to have something to differentiate, and we want something to integrate. And on the side over here, we're just going to have alternating plus and minus signs that are going to keep going down. And, well, on the top row here, we're going to put what we differentiate and what we integrate. So I guess this is kind of like the 0th iteration because we haven't really done anything yet. And on this next row, this is going to be our first iteration, so I'll put that down. So first iteration. And then on the second row, we have our second iteration. And then we're going to keep going down a little bit more further. But let's just stop at the second iteration first and see if we can find any patterns. So what are we going to differentiate? Well, I want to differentiate this 1 minus t over n. Because notice that n is just, well, we're kind of assuming it's some real number. So, and if we differentiate this a number of times, then we can kind of reduce the power little by little. But z on the other end is a complex number, so we don't really want to differentiate that. So let's differentiate 1 minus t over n raised to the nth power. But what are we going to get if we differentiate this once? We're going to get, well, this power jumps down, so we're going to have n, and then 1 minus t over n, and then this is an n minus 1. Okay, and we also have some chain rule happening on the inside. Derivative of the inside is just minus 1 over n, like so. Alright, let's differentiate this a second time. If we differentiate this again, we're going to get n, so these constants still exist, and then n minus 1 jumps down, and then we still have this minus 1 over n, but it's actually squared because, well, this is from the chain rule on the first differentiation, but since we're differentiating again, we apply the chain rule again, so we get minus 1 over n squared, and then we get 1 minus t over n to the n minus 2, so reducing the power by 1. So we can hopefully already see a couple of patterns emerging, and we'll discuss those later on. But as for our integration, we're going to be integrating t to the z minus 1. If we integrate this once, well, we increase the power by 1 and we divide by that new power, so it's going to be 1 over z t to the z. And then integrating this once again, we're going to get 1 over z and then z plus 1 because that's the new power, and we also get the new power at the top, so t to the z plus 1. So that's the second iteration, and we're going to keep going down as well. And we're going to end up landing at some kind of kth iteration. So some natural number k. And what's going to happen at the kth iteration? Well, let's try to look for a pattern over here. Notice on the first iteration, so I guess I'll highlight the number 1 in red. On the first iteration, we have n minus 1. And I guess I should also label this the 0th iteration as well. So 0th. This is kind of like n minus 0 up here. And then the first iteration, we have n minus 1. Second iteration, we have n minus 2. So what other patterns can we see? Well, if we have a second iteration, this power over here is a 2. And on the first iteration, the power is a 1. And on the 0th iteration, well, we can kind of see it's minus 1 over n to the 0th power. Okay, what else do we have? Well, everything on the inside here kind of remains the same, and everything on the inside of this bracket remains the same, but we kind of have this kind of factorial thing going on where we start with n on the first iteration, and then on the second iteration we multiply by the number that's 1 below. Well, notice in the first iteration we just start at n and then we don't multiply by anything else, but on the second iteration we go down 1 step. So if you take a look at this 1 right here, this is basically 2 minus 1. So we start with n and we stop at n minus 1, and that 1 is exactly 2 minus 1. And on the first iteration, well, this is n minus 0 pretty much, so we have 1 minus 1 over there. And on the 0th iteration, well, it doesn't really make sense to apply that rule. But let's try to apply the pattern that we found over here to the kth iteration. Well, we're going to have n, and then n minus 1, dot dot dot, all the way down until n minus, and now this whatever constant in here is 1 less than k. So we're going to have n minus k minus 1, like so. Alright, let's check for any other patterns. Well, on this factor over here, we have 1 over n raised to the first power, 1 over n raised to the second power, and that's basically dividing by n, then dividing by n squared. And on the kth iteration, we're just dividing by n raised to the kth power. And I want you to notice one small thing. We don't really have a plus or minus here because this is alternating plus minus, but it actually doesn't matter on the kth iteration because if you notice over here, on the first iteration we have a minus, but that's cancelled out by this minus 1 to the first power. So this whole thing is positive. On the second iteration, this is a positive sign, but over here minus 1 squared is still positive. So it doesn't matter which iteration you're on, it's always going to be positive. So these negatives kind of cancel each other out. So you can just assume that the kth iteration is positive overall. And then as for this factor over here, well, we have 1 minus t over n, and then we have n minus, well, n minus 2, this 2 matches up with the second iteration, so over here we should have n minus k. So I'll just highlight this over here as well. Alright, and let's see what happens on the integration side. Well, this pattern is a little bit more easier to see, so a little bit more intuitive. So if you look at, say, the first iteration, well, this is kind of like z plus 0. And on the second iteration, we have t plus 1. So as you can see, these numbers that I've highlighted in red is just 1 less than the iteration value. And similarly on the denominator, we start with some z on the first iteration, and then on the second iteration, we also multiply by the 1 below. So we can kind of generalize this on the kth iteration. We have 1 over z plus 1, and then dot dot dot, all the way up until z plus, I guess I'll just highlight this in red, so this is basically 2 minus 1. So over here we should stop at a k minus 1, so z plus a k minus 1, like so. So those are the constants, and as for this power term over here, we have t to the z plus, and well, this 1 is exactly 1 less than the iteration value, so over here should be k minus 1. So we found the pattern, the general pattern when we integrate that function. Alright, next what I want to do is I want to take a look at the nth iteration. So nth iteration. So what happens at the nth iteration? Well, this is just some natural number n, and all we really have to do is plug n into these k values over here. So what happens if we do that? Well, on the top we're going to get n minus 1, dot dot dot. Now if we plug n into here, we're going to have n minus n, which is 0. Then these two negatives cancel out, leaving us with just 1. So we have n minus 1 all the way down until 1. So that's basically an n factorial, but I'll just leave it as in this form for now. You'll see why later on. And over here we have division by n, and this k turns into an n. So we have n to the nth power. And as for this term, notice that on the nth iteration, we're going to have n minus n, which is 0. So this whole thing is something to the 0th power, which is just a 1. So in fact, when we get to the nth iteration, we're just left with a constant. And on the integration side, what are we going to get? Well, we're going to get 1 over z plus 1, dot dot dot, all the way up until z plus, now we're plugging n into this k, so we have z plus n minus 1. And as for this power, we have t to the z plus n minus 1 as well. Alright, so that's the nth iteration, and the nth iteration is in fact a really nice one, because over here we end up with a constant, and if we differentiate this thing one more time, we in fact get 0, which is really nice. And I think I should mention that we can assume n is a natural number. So n is a natural number that's just tending towards infinity. It has to be a natural number in order for all these things to work out. So let's take a look on the next iteration, so the n plus 1th iteration. What's going to happen there? Well, this is just a constant, so if we differentiate this thing one more time, we're going to get 0. And as for the integration side, well, we're just going to, well, instead of having this, we're just going to plug n plus 1 into the k. So what are we going to get if we do that? We're going to get 1 over z plus 1, dot dot dot. Now if we plug n plus 1 into here, well, this plus 1 and this minus 1 will cancel each other out, leaving us with just z plus n. So all the way up until z plus n, like so. And same deal over here, the minus 1 and this plus 1 will cancel, leaving us with a t to the z plus n. And this is where we're going to stop with this di method, because we've reached this is 0 over here, which means there's no point in going further because every time we integrate across, so each row is kind of like an integral, we're just going to be integrating 0, which isn't really interesting. So what is the result of this integration by parts? Well, what you do is you take these diagonals and you multiply them together. So all these diagonals over here, you multiply them all together. And of course you stop at 0 because once you multiply more diagonals, then you're just multiplying by 0, which isn't that interesting. And you multiply all these together and you write out what you get on the other side. So if we multiply all these together, what are we going to get? Well, let's see. On this first diagonal, we're going to get minus, I guess I'll just write, I'll write this first. So 1 over z, t to the z, and then we have minus 1, actually, that's just minus 1 over n to the 0, so there's no point writing that. But we get 1 minus t over n to the nth power, and we evaluate this on the bound, so from 0 to n. And if we do this for the first diagonal, well, if we plug n into here, we're going to get n over n. And remember, we're plugging values into t because we're integrating with respect to t. So plugging n into this t, we're going to get n over n, which is 1. 1 minus 1, which is 0, so that kills off the whole thing. So this n gives you 0. And as for 0, if you plug 0 into this t, well, 0 raised to anything is 0, so you also get 0. So overall, this first diagonal, the value is 0. And as for the second diagonal, let's just try to give a bit more space. We're going to get 1 over z, z plus 1, t to the z plus 1, and then over here we get n, minus 1 over n, and then 1 minus t over n to the n minus 1, and we evaluate this from 0 to n. And you can check for yourself, if you plug n into here, well, you're just going to get 1 minus 1, which is 0. So nothing happens over there. And if you plug 0 into here, well, 0 into this t gives you 0. And you can kind of check for yourself that all these diagonals give you 0, except for the very last one. But we will look at that later. So for all of these other diagonals, you're going to get something in the form b, where b is some constant, times t to the c, where c is another constant because we have t raised to some power c. And then we also get this other factor, which is 1 minus t over n to some power d, where d is also another constant. And if we evaluate this from 0 to n, well, again, plugging n into here, we're going to get 0 in this factor. Plugging 0 into this t, we're also going to get 0. So it's just going to be a 0 there. And that, we're just going to get zeros all the way up until this very last diagonal. And the reason why we don't get 0 here is because this thing is just a constant. So that we don't get this extra factor of 1 minus t over n. So in fact, something special does happen there, and let's see what happens. Well, if we multiply both of these together, this is going to be a little bit messy. But we're going to get n, and then n minus 1, dot dot dot, 1, over, now I want to put this n to the n here, so n to the n, and then we also have z, and then z plus 1, dot dot dot, z plus n, and then we multiply by t to the z plus n, like so, and we evaluate this from 0 to n. Well, if we plug 0 into here, into this t in fact, we just get 0. And if we plug n into here, well, actually nothing turns into 0, so we do get some meaningful result out of this. So from this whole integration by parts, we add all these the values of these diagonals up, evaluated at its bounds. And the only thing that really remains, well, we have a bunch of zeros here, this bound turns into 0. So overall, this integral evaluates to, well, we still have this limit as n approaches infinity, and we just have this expression evaluated at n. So I'll just write that down over here. So n minus 1 dot 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 1 over n to the n times z, and then z plus 1 dot 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 z plus n, and we have t to the z plus n, but we plug n into this t, and we get n to the z plus n, like so. Alright, so that's basically the whole integration by parts done, and now we just need to take a look at this expression a little bit more. So that was quite a bit of work, but we've gotten quite a nice expression out the other end. So let's keep taking a look at this expression. This is a z plus n. So we can actually do some simplifications right away. Notice that n to the z plus n is the same thing as n to the z times n to the n, and we can cancel n to the n with n to the n over here. Next, what I want to do is I want to kind of separate this fraction out a little bit. So this is the limit as n approaches infinity of n to the z divided by, now I'm going to drag this z out. And the reason I drag that z out is because what's left, we can form a little bit of a pattern. On this numerator, I'm going to basically reverse everything. So we're going to have 1, and then we're going to have 2, dot, 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 and then n minus 1, and then n, like so. And this is divided by, now what happens on the bottom? Well, this z we dragged out, and we're left with z plus 1. And this is basically counting up z plus 1, z plus 2, all the way up until z plus n. So the next one would be z plus 2, dot, 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 and then z plus n minus 1. So that's the term before this z plus n, which is the very last one. So we have this kind of fraction over here, so rubs it out. But notice we have a bit of a pattern going on, and we can represent this as some kind of product. So now we have the limit, this is an ugly n, so limit as n approaches infinity of n to the z over z, and now we can represent this as a product. So we have a product of a bunch of things. Well, first of all, if you kind of split this product up like so, you'll clearly see the pattern. So we have some number over z plus the same number, and then we count up 1, so 1 plus 1 is 2 obviously, so we get 2 over z plus 2, and then so on. So let's choose an index, let's call it k, and k, our index is going to start from 1, and notice we start from 1 and we end at n, and on the inside of this product we have the k value divided by z plus the k value. And this is basically it. So this whole big fraction, we can collapse it down into a single product. And now, I guess all that's really left, you can move this z out if you want because it's independent of the limit, or you can leave it in there. But overall, this is the Gauss representation for the gamma function, which is gamma of z is equal to 1 over z times the limit as n approaches infinity of n to the z, and then product from k equals 1 to n, k over z plus k, like so. And that's basically it for this video. So in the next couple of videos, I will be deriving the Euler and the Weierstrass infinite product representation for the gamma function, where we start from this definition. But yeah, that's pretty much all for this video. Hope you guys enjoyed it, and I'll see everyone next time. Bye bye.